understanding how I do that. I don't know how any person can do it. But that doesn't mean that machines will not be able to simulate that video of the next 3 days in pixel. We've learned, we always go back to the human, but I think it's important that we keep in mind that machines are capable, and this field knows it very well. We're capable of doing things with machines that humans are not capable of doing.
Maybe I can. Okay. I'm not comfortable with talking. Maybe another thing you can do is just create this pixel level simulation of what's going to happen, and then look at what actually happened. And if you see some differences between what you predicted and what actually happened, you can have a surprise element and then learn better for the next time.
That was actually mentioned by Hamlet. So there have been experiments where people have used these kind of like pixel losses to train representations. For example, in one of our papers, we actually trained visual representation with this whole thing that if you cannot predict, you need to do a loss, that propagate the loss. And you can then try to compete on standard Pascal VOC challenges by training with just these kind of video prediction losses. So that's, I think, what Hamlet kind of mentioned that.
Maybe can you comment on your different perspectives on simulation, like physics-based simulation or games, etc., to transition from in the lab to in the real world, either robotics or vision or whatever. So importance of simulation in your own vision.
So there are different ways of thinking about it. The obvious reaction is, well, it's not natural languages, let's not use it. I tend to disagree with that point of view, mainly because if we exclude simulation, there are things that are too expensive to do in real world. And for some of those, we might be able to do it for a limited number of training data, but not everything. So these days, I tend to sort of advocate the strategy of at least start off your model on some carefully designed simulation domain, then migrate it to real data. And I think this has been the strategy that worked out pretty well for a couple of things that I've shown. Again, I'm not going to make a claim that we can just naively translate or transfer what we learn in simulation images, but still we can actually we can do a lot of heavy lifting by just training on simulation. Given that we need to be extremely careful about the simulation domain, what are we training on it? Sometimes you actually need to make things as good as possible intentionally, because this way you can force your model to only learn about what you want it to learn. Because when you go to simulation, you have to be extremely careful about not being confused with the biases introduced by the simulation, either by the artist or the game. If you're careful about that, I believe you can do a lot of different things.
So what I think is that there are two components. One is that let's think about what's the ideal situation. The ideal situation is that we have actually a very, very good simulator that's closely approximate the real world. So as close the simulation is to the real world, it's better. The second one is that probably we need some kind of high level, some representation that somehow can link between the two. So I mean, the better we can do these type of jobs, we would actually get more benefit from simulation to the real world. That's, yeah.
I think I would say that how much would simulation transfer to the real world is unknown. It's a very open research question. There are a lot of labs trying to see if they will actually transfer or not. And I think there is enough diversity in the field that there are people who are doing just learning on the real data. There are people who are doing learning on simulation, and then there are people who are trying to have simulation transfer to the real world. I think this is something which I completely believe time will tell, which is the right direction to go. I mean, I agree that simulation, you can have much more data, but simulation is still simulation and real world data is still real world data. So it's something I think which is unanswered question. How much will it transfer? Will it transfer? Will it be ever useful to do anything on simulation? I think this is something only that time will tell where how much do we get out of this simulation.
All right. One thing that came up earlier in the day was how do we actually measure how well unsupervised algorithms are performing, especially if you're doing something like learning representations in an unsupervised neural network. How do you then measure how well it's performing? Do you measure it on some new task that you use this as use your first trained network as an initialization for, or are there better ways to do this? Should we agree as a community on sort of a library of tasks that we measure this performance on? Yeah, what are your thoughts on that?
I think, so I have been having this discussion with Philip and other people as well. I think there is definitely a need to come up with benchmark. Just taking these, by the way, most of us, what we do is we do unsupervised learning. Then we say, oh, we will then fine tune with Pascal. And you would never know how much actually learning was done by Pascal and how much learning was actually done by the unsupervised stuff. And so that is why what you would see is that some networks do good on one Pascal dataset, some networks do better on the other. And that's what at least I have seen in my multiple unsupervised works. There's not one network which will do good on every fine tuning. I think the other thing which is very conflicting is this whole fine tuning process really. A good representation might not be a best representation for fine tuning essentially. So I think we just need a suite of tasks. Recognition could be one. We definitely need something like nearest neighbor to just do it. And then maybe the third one has to be something of actions, since a lot of unsupervised stuff is built towards actions essentially. Those are the three tasks I can think of, and I don't know whether.
I agree that it will be helpful to have multiple suites of tasks. Also, it's actually very important to think about whether this representation is compatible to multiple tasks. So ideally, we want to have a representation that's good for unsupervised learning, but also that's good for some other discriminated tasks, such as classification. So in often the case, it's not really true in a sense that if you try with a combination of this reconstruction loss with the classification loss, usually you have to sacrifice one way or the other. So actually, I have some paper at ICML this year that actually shows that using some autoencoder in a style of deconvolutional net. So you have convolutional encoder and decoder, where you keep track of the switch activation map. So you keep track of which unit is next pulled and so on. You can use that to decode it back. And the high-level conclusion is that you can basically get almost like the perfect reconstruction of the original input. And so that is actually using the pre-trained convolutional like BGG network for like classification. So it was actually purely supervisedly trained feature that somehow turns out to be also good for reconstruction. So in that case, these features are not really like conflicting and in conflict between the two different tasks. So potentially like developing some representation that's really able to do multiple tasks without really sacrificing one or the other to be also interesting research question.
I think fundamentally what we need is lots of tasks, and we need to free tasks the same way that we free modeling and we free computation to the masses. So I would be a bit hesitant to constraining tasks. Benchmarks are always useful, of course, but we do need more free tasks. One of the most powerful definitions of AI is the one of transfer, being able to transfer from one task to another task. And we cannot test that definition unless we really have systems that can exploit structure learned in one domain to another domain. One example that I like, that I think of when walking down in Amsterdam, is you look at, you're walking down over a bridge, you look down, there's that substance there, and that substance has a normal surface phenomenon. And then perhaps a child will go there and play a timer up to one end and do this motion with the rope. And then we'll see that that same phenomenon is observed as the phenomenon that was in that substance. And then maybe we'll give it a name, wave. And we'll start studying that waves have a sort of height and distance and so on. And once you develop that, you can communicate it with other agents. But you kind of needed to experience different tasks to be able to extract that concept, to be able to communicate, to be able to generate a symbol, the word wave, to communicate it with other agents. And once you have the symbol, then you can just manipulate the symbol further and come up with this thing that, you know, an electron is this wave, is the absolute value of this wave of probability. And you get into all sorts of, you know, extensions that are possible through that symbol acquisition. That kind of strategy is only possible if you have many tasks.
I don't think we can free us from tasks or things being specific to tasks, but maybe at some level or at some layer of abstraction, there's some way to transfer things between tasks. But really, we are seeing that actually you need task-specific data in robotics, at least, to fulfill a specific task. Really, we need to extract different features, maybe even different modalities to be able to be successful in those. So I think we cannot completely free us from this, but maybe there are some level of abstractions like physics or how your own body works or things like that that can be reused.
Before switching, I'm going to add to the confusion. I think before answering your question, you need to answer me what are the key characteristics of a good representation? What it actually means to have a good representation. Pre-deep learning era, we tend to call it discrimination. These days, it cannot. People used to call reconstruction as a key characteristic of representation. I think that doesn't apply as well. But I think we're actually one step behind your point, which is we don't even know what makes a representation a good one. And before defining that, most people evaluate.
I guess it's kind of specific to different domains as well. You could, for instance, make it slightly broader than just saying ImageNet category recognition. You could just call it, maybe your task is to train a representation for recognition. And in that case, maybe you can have a suite of different recognition tasks. Yeah.
The first one.
Well,
Yeah.
now it's okay. Okay. One key question is that what we see in natural intelligent organisms is that they are mostly multimodal and they use multimodality to gather information. But neural networks, I know it's a vision conference, but neural networks are usually trained on mostly, at least in robotic tasks, for vision. For example, in the work of what happens if you have turned the modality of the force into a picture to feed it into a convolutional neural network, which seems like a bit of waste of data. I'm thinking what are the ways to incorporate the multimodality of the data in order to learn better from?
The short answer is multi-color representation. You have a color modality. I agree with the point that you raised that neural networks are actually with one modality. Many tasks, question answering. There are examples of multimodal learning algorithms that work. And it's always a question of at what level you want to combine them together. The typical solution that works these days, again, it's not a just one common thing people try, it's a tower for each modality and then merge somehow.
And then the vision overcomes.
Well, the merging happens through layers, and your layers supposedly can learn how to use things together.
I think you're right. I mean, so for example, the first talk I'm sure today we talked about like multimodality being one of the principles of learning, especially in these self-supervised systems. And I think it was just until now, vision was not working. And I think now finally we are starting to at least feel like vision is working, if not working. And I think so now things will start to move in that direction where we will move towards more multimodality. For example, I have been looking at haptics. MIT has been looking at audio. I mean, so they have been trying to train visual representations from audio. That's another example of a multimodality. So I think things are now moving in that direction, and very soon this will happen. So this, if I have to pick up like some of the interesting areas to go to, I think this is one of the definite interesting areas, like haptics and audio, and how do you basically all this redundancy in the data, Like whatever haptics is saying has to be coherent with the visual data. Whatever audio is saying has to be coherent with visual data. And I think if we can, I think that would be something now people will start to look at. And the first things people are trying is, of course, the towers, like different towers, and make sure they are coherent with each other. But next stages will be much more interesting than specific data.
Well, I guess for the vision conference perspective, I mean, the concept of multimodal learning is probably relatively new, but I would say in deep learning, there has been also lots of work in multimodal learning where you can combine images and or videos and audios and also text and so on. So, but I guess for in the vision community, there has been also growingly extensive work on combining text and image. So caption generation is one good example, and yeah, there are so many similar tasks. So I think it's growing more attention, and probably it will become more bigger efforts at the whole community. But I would say that the concept of multimodal learning to me is a very central component in learning on intelligence, in a sense that if you think about just learning common sense intelligence, really like high level intelligence from a single modality, it's going to be extremely hard. So actually I was talking to some experts in speech, and we thought about, okay, well, how much data do we need to actually learn the state-of-the-art language model in speech? It turns out that it's much more than the amount of all the speech, continuous speech you can listen in 20 years worth of time. If you are just human listening to 150 words per minute, 24/7, if you do it 20 years, it's not good enough to train a good language model. So, I mean, there are lots of evidence that it's probably not just a single modality, but actually more a combination of different modality. Especially if you're aiming toward learning really high-level common sense intelligence. But obviously, that's going to be extremely hard problem. So, and also we haven't really tackled in the deep level toward that problem. But I think in the long run, that will be very, very important. It will be essential component.
Hi, I have 2 questions. First one is, has there been any work done regarding representation using time sequences? In other words, if a child picks up a toy and he looks at it in various angles, is there some equivalent thing in computer science? And I guess I'll ask the second one after you've answered the first.
So from the viewpoint of robotics, there are many different representations of actions that stretch over time. First one that comes to mind is dynamic motor primitives, right? That are really encoded with them explicitly with time, and to which you can attach different multimodalities or multiple modalities really to encode how these actions are not just generated kinematically, but also how they should feel. Right? So this has been done really. By the way, haptic data has been worked on for 20 years in robotics. So there's lots of work there, and I think now that learning and vision has been advancing so much, it's really interesting that this get together. So this just as a side note to the previous question. Yeah, and in terms of time series and vision, I guess there's a lot in action recognition, but I'm not familiar with this. So if anyone else has something to say?
Thank you. The second question is, oh, I forgot. Never mind. Thank you very much.
Do you think we need robots to teach us about vision? Maybe. Okay, the question is, do you think we need robots to teach us about vision? Or is it always better just to have a grad student instead of playing with a robot and spending tons of time and money doing that, just having to go around and label the world. Yeah, I would like to hear your opinion on which is the better of the two, or is there a mix between the two?
So I'm a roboticist. I love robots, and I find them fascinating. So therefore, I think, I mean, I like to know and see what they can tell us about us, right? Because we are embodied, we have visual sensing, tactile sensing, we can control our motion. And the question, or the fundamental interesting question for me, is how we developed these amazing capabilities that robots just simply don't have right now. And well, the good old Feynman thing, right? Like, he didn't understand the system, so he had, before he built it, actually, right? That's the same for me. So that's my personal opinion. I think there's something about an embodied system that controls its own action and observes the concurrent feedback in any sense, visual or tactile, whatever, or audio. That makes at least us somehow work, but we don't yet know how. And robots are amazing tools and complicated tools and frustrating tools sometimes to understand that.
I mean, I would strongly like to believe that, although I have no proof of any sort, but that robots are, I mean, the physical interaction with the world is really, really important. I mean, at least in our experiments, we have seen that physical interaction really helps, like provides very strong supervision in training visual representations. But I think I would like to take it a little bit higher in the discussions and say that I think what robots bring, or what this real interaction with the physical brings, is the power of intervention. And I think that is something completely missing. If you are just looking at passive data, you cannot control the data. Really control the data. I can basically say, I'm only going to change one parameter in the whole system. Everything else is the same. I'm just going to change like a little bit more force. What happens there? And I think so. This whole nature of intervention, like keeping lots of variables constant and just changing a field, is something which is very, very important for causality, at least I believe. So I think, I mean, at least when I talk, it seems that robots should be very, very important for training visual representations. But of course, experimentally, we have only very, very weak signals which are pointing that this is really true. Probably the biggest reason being that we are still not as fast as collecting more data by just labeling. Hopefully, I think if we can pool the data from all the robots in the world, then I think we can be faster than your mechanical Turk or something. There have been people have been talking about it, but somehow it has never really. But I think that's also because there's not one common robotic platform which everyone uses. Now that these
Which is good. I don't want to use a backstory.
but you can use a fetch. I mean, I don't care about, as a vision person, I don't care about what robot, but I think at least as long as there is one robot which is there at least 100 different locations, and they all 100 locations decide to pool the data together, whatever they generate. I think that is what we need. We need to basically create this crowdsourcing of robots rather than just crowdsourcing of humans.
But then as soon as you say you record the data as replay, right, then it's just observation, it's no longer action, right? Then you're just collecting data. And you can just have 100 grad students do the same thing and record how they, like you can have a little sensor in the grad student's hand and you can go touch things.
I mean, by having this 100 different, if we are talking about 100 different words, I think they will still have a very good way of searching through the space. I mean, they should be able to they should be still running a exploration policy or something which will really help them to get this intervention that say that it should not be just a random search at the end of the day. But what I still want is at least 100 different locations so that the diversity of data is there as much as we can. Because I think one of the biggest problems in robotics, at least what we have felt, is that because we are only collecting in our own lab, we are only seeing a very specific kind of objects. Even though it still works, like yesterday I was showing the results, and it still works for classification and retrieval. If I could actually diversify the robot data, I think that would give me much bigger gains, at least that's what I do.
Now, to play the game a bit, what temperature do you think this guy is? The guy that I'm holding. First, what's this?
Well, it's a microphone. It's 21 degrees. It's the temperature.
How do you think it feels?
Good.
What will happen to it if I throw it in the canal?
It will be very loud if you throw it away. If you throw it in the canal?
Yeah.
Yeah, it will probably break.
Do you think there are things of this nature on Mars?
Probably not yet.
Could I kill a giraffe with it?
You could try.
Could I kill a mouse?
Yeah, probably.
Do you think dinosaurs played with devices like this one?
All right. No.
So I could keep going and going and going and going and going. The amount of labels I can generate for this device is infinite. So that grad student would have a really tough job. So eventually you do need to come to what this workshop's about is understanding the properties of this object. And it's only through understanding the sort of being able to manipulate and understanding what it does to my muscles, what it does to my eyes and my vision and so on, that I eventually start getting an understanding of it. And it took a long time and a lot of symbol creation and symbol manipulation for this object to come to the Earth. And that's why you can figure out that it's not on Mars and that dinosaurs didn't play with it and so on. So I think the path to AI cannot be one of link.
Okay. Well, we agree on that one.
I think we misunderstood those questions. I think he has a way of programming grad students.
Or maybe you were referring to the difficulty of doing robotics research because when you robot X, it changes the data, and you cannot have these data sets necessarily.
I mean, I agree with all of you that in the very end, we probably would want to have a robot that looks at the object and understands it. What I'm more interested in is right now, do we actually make more progress by trying to go through a robot, or is there more to be gained by actually still having a grad student label things? I mean, if you have a grad student label, I threw this in the canal and it broke, and I threw the other thing in the canal and broke. Well, I mean.
So I don't understand something from a grad student labeling things and then training some crazy architecture. I mean, I can do that and tune some parameters and blah, blah, blah. But I haven't learned something about the process of, I don't know what to call it, intelligence, autonomy, cognition, or whatever you want to call it.
But did you learn that from a robot right now?
Yeah, I think, well, right now, I mean, no, we have a bit to go, right? But I think it's closer to what we do. So therefore, we can test some of these concepts that come from cognition and embodied cognition on a robot and see what it can give us. And certainly you see that through, like what Abhinav showed, right? Through self-supervision, you can learn a lot of things that are particular to the robot and not to a grad student being given a particular task on what to label and having a particular assumption of what is actually important to label and all these things, right?
Right. Well,
I think it also depends on the task. I mean, you're obviously right. There's a trade-off here. ImageNet's a good example that the grad student labeling pays off, whoever labeled it. But natural language understanding, I think, would be very hard to do just by labeling.
thank you.
So you guys have talked a lot about long-term anticipation, like days from now, we're asking really abstract questions. But most of the models that you guys talked about, at least the ones I saw today, were looking at very short-term intervals, using these latent representations from CNNs. You guys have brought up symbolic representations, but that didn't really play that big of a part. What do you think the role of symbolic representations will be, say, 5 years from now? Do you think that will make more of a comeback, or do you think we'll stay with more of the latent representations?
Symbols will come back, but symbols are not in the mind. Symbols are in the world. That's, I think, a distinction with classical AI. We manipulate words. Words are symbols. We write books. We use those books to teach other people. Symbols are extremely powerful, and it's through symbolic manipulation that we're the one species that is surviving while the other ones are dying. So obviously it will come back, because eventually we'll have to understand how we accelerate our understanding of the universe by symbol manipulation.
also agree that the symbols will come back in a sense that basically, ultimately, in order to solve vision or any intelligence task, you need to understand how the world works. That's actually a fundamental level of intelligence to solve vision, not just doing object recognition or segmentation, but really you need to understand the world. And probably, probably the best machinery for doing that, at least in the conceptual level, would be some kind of logic or maybe cursor logic or some kind of common sense that's represented this way. This type of approach obviously have flaws because you cannot really represent these things with deterministic logic. So maybe we need some more like a probabilistic notion of logic. But then there are some also lots of work in Markov logic networks and so on, but it's not clear whether they are the best approach. I don't know what will happen in the future, but probably we will need to come up with some representation that's being able to do this type of kind of logical reasoning. That is also compatible with the deep neural network, because deep neural net is really driving force of the perception and all kinds of recognition. So this is an open question, but I think it will come back at some point.
Just to echo on the same point, I'm going to repeat the same thing. I think what deep learning is failing at the moment is reasoning. And when we go to real reasoning, the combinatorial space is just exploding, and we don't have the machinery to handle that at the moment. A form of explicit reasoning or explicit representation would re-emerge. Is that going to be symbolic, logical, or in different form? Is that going to be different? No. But an explicit representation, my guess is will come.
It's weird, the argument of saying symbols come back at the workshop, where the justification, the main justification of the talks we've seen is about grounded cognition. And the theory of grounded cognition and embodied systems, it arose in opposition to symbolic reasoning. So if you look at Laurence Barsalou's theories, and later the neuroscientific evidence that supported these theories, showed that we don't have a symbol for chair in our head. When we think about abstractly about the chair, actually we have the same kind of activation. So I know it's not an explanation of how the brain works, but we have the same kind of neuronal activities as when we sit on the chair or when we look at the chair. And that's the argument for grounding cognition in perception versus, and the interaction loop that we discussed about before, it goes in this direction. And so saying that we're getting back to symbols means that I fail to reconciliate a bit the two things, the grounded cognition and the symbols. So maybe you can elaborate on what you think symbols is going to make a comeback, although grounded cognition is the way to go.
I'm not really expert in this neuroscience literature, so I cannot say much about that. But basically being able to make this low-level, like pixel prediction, is actually a very good way of grounding things. So you have some high-level features that are, basically you can think about some encoder from your observation. And then you make a prediction in this encoder feature space. And then you're not really sure whether it's good or not. And one good way of really verifying it's good is that you just project back to the raw observation and make sure it's kind of compatible. So I don't think there is any conflict between this sort of grounding versus symbols. So what I'm saying is that probably the most advanced technique so far is not really using explicit notion of symbolic reasoning or some kind of common sense reasoning, but I think that can be potentially augmented to what people are working on. So we don't have it now, but I don't see a conflict between the two.
So I'm a bit confused about the question because I thought computer vision was all about symbols and still is. All these discrete labels that are being used and trying to objects to be recognized, all of these are symbols for me. So maybe I'm not quite understanding the question, or maybe you're referring to the pixel level predictions.
Symbols in computer vision before, but when you define an object like parts, you say a chair instead of defining it by examples and learning about it. So say a chair is 4 legs. Arranging that position, etc., and you try to reasoning with first order objects. And this has failed, and the machine learning era has enabled to basically learn all the very complex parameters of appearance without having to actually describe the entirety of the logical relationship with the constituents. So by symbols, I mean legs to represent chair, and by grounded cognition means I have a thought vector a la Hinton style that represents, basically summarizes all my examples that I've seen and that represent the appearance, although I can't trace necessarily back to chairs or maybe to legs, or maybe I cannot.
So the two don't disagree with each other, and you're absolutely right. But here is the thing. You do have the concept of a chair, whichever form of pattern activations you have in your hand. And that gets activated when you sit on it, and gets activated when you see it. When I say the word chair, it's activated. But we do have this percept, or this action, this tool, these various tools that we use, like the written word, that we use as a pointer, as a reference to that concept. If I want to put a concept in your head, I will pick this reference, I will produce the symbol, or I'll write this down, and that symbol, that tool that exists in the world will be enough for me to activate that concept in your head. So I see the symbol as a thing in the world that I manipulate to activate different concepts in your head. And some concepts are much easier, like chair. Classes are like the first level of abstraction. So classes are already abstractions that are simple. So it's true that in ImageNet, we've artificially made the problem easier. But as we go into a higher level, I think we sort of start getting abstractions of abstractions. And that way we kind of get into the sort of economical theories that we have of things and science and so on, or different concepts that were like things like God, or the concept of a concept, recursive notions. And we're able to talk about things like 10 to the 100 minus 3. Which one is bigger, 10 to the 100 minus 3 or 10 to the 100 minus 5? You can do that computation because of symbols, not because you have those concepts in your head.
Hi, thank you very much for your presentations. I'd like to ask, in your slides or in your presentation, you have mostly a free world scenario. So if you would like to do more higher level causality inference, would you be able to still do that with this scenario, or you'd like to have some sort of instructions given to the agent? So for instance, let's say you wanted to learn how to turn on the lights. Probably that's much harder than just letting it do stuff forever, right?
Let me repeat the question just to make sure I understand it. Are you saying that there are tasks that are harder than navigation, let's say? You want to learn them through interaction. Is that what you're saying?
You could say that. Another way to see it is that when you go first is the jar and you push it. I mean, that's an action fault, but it's also sort of cause and effect thing. Perhaps you can also model it like that and avoid having to learn all possible variations of how things move around.
I think no one is claiming toward training all possible variations of things. What I was hoping at was learning an abstract representation that allow me to learn those kind of abstractions in a convoluted, embedded way. But ideally, these are the things that I'd like to learn. There's some sporadic evidence that some of them can be learned. Does it generalize to more complicated actions? I still don't know that. And how expensive would it be to do more complicated actions like making coffee? We're still a bit far from that so I can actually answer that. But I'm hoping that through these layers of abstractions and lots of interaction, you should be able to learn something. Also, the roboticists have this group of roboticists working on imitation learning. And that's a big part of things that we're exploring at the moment, and I should also couple that with interaction.
In this situation, how can you evaluate like more complex stuff, like because like make coffee, or will be good to.
So there are different ways of thinking about it. For example, one trivial way would be the number of steps that you would take to make a coffee. If you want to start pouring a table into a cup, you're going to basically waste some cycles, and you can be penalized for that. You can also be penalized semantically for the kind of affordances you get wrong. I would imagine there are also more complicated ways of working.
Maybe I can. So it's a very simple question. Suppose we have as much data you want and as much computational power so you can process it and you don't care how long it takes or it's very fast. Do you think, and there are no labels whatsoever, just images of images. Do you think you can learn, a system can learn automatically a representation, a compact representation of the world? For example, figure out this 3D.
So there's the so-called Bremerman limit, right, of computation. So I know you said, like, let's assume we have unlimited computation power, but I'm not sure if that makes sense. Because there is not, for sure not, to search the entire space of input mapping to output mapping. So I'm not sure, like where are you trying to get at?
Please use the mic.
Basically, what kind of information is there, right? So if you have infinite computational power and infinite amount of data, then can you actually do it, or still you can't do it? Besides what you can actually do.
Do you have? I mean, I think this takes more questions. Do you have like infinite amount of all kind of data, or do you have only infinite kind of images? Or I mean, so like, you see basically what I'm saying.
Just images.
I think, I mean, yeah, that's what my guess would be. None of us has really tried infinite.
Jumping spiders can see 3D. All animals can see 3D, so that's proof that, well, not all animals,
But they don't start with infinite amount of computation and infinite amount of.
It's not even needed.
I would, so here's the comparison. So you have the two cats in the carousel. So imagine taking the one in the basket and taking her around the world. Okay, so no interactions, just images. Will it learn that the world is 3D, for example?
No.
Okay. Why?
Because that's what the experiment showed, right? So these passive cats, they could not perform simple tasks. Like they were basically falling off cliffs. These were like simple cliffs and stuff. They were running against obstacles. So when you take them out of this basket.
But that's a cat. I mean, if you have infinite computational power, is it there?
You need a task, though. There has to be a task, otherwise it's passive. If there was a goal, yes, there would not be.
So for 3D, I could disagree with Jeanette, but I would say probably just learning a representation of 3D is possible without any supervision. But maybe the next question is that why is it useful? And maybe in terms of semantics or functional level, and it's unclear whether we can just learn something very, very useful just looking at purely unlabeled data. So, and also if you think about how humans learn, we are not fully unsupervised. We get teachings from parents and teachers and so on. I mean, although these are not really like a huge amount of the data that we receive, and probably more than 90% of the data that we receive is unsupervised, but we still get some very critical level of supervision. So probably, yeah, to be fair, I think it's maybe too hard for computers to just learn everything unsupervised. Maybe it's also not practical direction, but I think again, if we can still learn a good representation without too much labels, too much annotation, that's what we are trying to do. But personally, I'm not necessarily saying, oh, we should just remove all the supervision from our learning.
I don't think just images is ever going to be enough supervision. That's why I asked, like, if you have other kind of data. I think the supervision will come from multimodality rather than if you have to do supervision. It's going to be really very difficult to just have data and images. You need some supervision, and maybe you need supervision in time. That basically, I'm looking at the same object as I'm moving along. Things like those. Just million jumbled images or billion jumbled images doesn't seem like at least right now it doesn't seem like it will reach any. We are labor propositions.
So if you imagine a universe with this an infinite amount of images coming by, and a system that is just maybe just producing every image, that has no purpose, there's no task, because the task is a label. But if there's nothing, no, it shouldn't have free structure. But the moment you insert a task, it will. The moment you insert an attractor that forces it to happen, it will happen.
So the task is to build a compact representation.
Okay,
We can talk.
so the 3D representation could be built if it was useful for something, right? That's, I guess.
My match is yes. Would be compact representation, compression, 3D might provide some compression. Comes out the compression.
So one thing that it seems one aspect of the themes of the workshop that we've only kind of touched on very lightly is while we've spoken about agent actions in a world, in a agent like a free agent acting on a world, we haven't really touched upon agents, for instance, being social or interacting with each other, etc. We've spoken about, for instance, competition for instance, the robot wars work, or even DC GANs, and GANs themselves can be seen as, or generative adversarial models can be seen as, machines kind of helping each other do better. But are there sort of this clearly seems to be only sort of the top of the, like, scraping just the surface of the problem. So there seems to be a lot of scope here. Do you have general thoughts on these directions, or how this could proceed, etc.?
I think, just on this question, I'm going to give a very generic answer probably. But I think this is like a very interesting question, like to model. A lot of people call it theory of mind and stuff and so on. I think it's really interesting to see other people in the scene and to try to use like a social content to learn. But probably I think it's not the intelligence of a 3-year-old or 4-year-old. It's beyond that. Something most of the cases. So I think the question is, what do you want to develop? If you want to develop the intelligence of a 4-year-old, 5-year-old, I think at that point of time, social is probably not playing that. If I understood your question, like that kind of social elements, they're not playing that big of a role.
There is this idea, for instance, that communication is kind of the the holy grail of intelligence, the ability to communicate. Perhaps not in semantic terms like a communication with a human, but communication even among just agents that are out there.
And stuff and all these,
yeah. Or teaching, or even like transfer learning can be thought of as sort of a communication between two different agents. So sort of even interactions among agents, sort of working towards that itself can be useful in several different ways. That's kind of what I was getting at with the question.
So there will be a few papers at NIPS this year on learning communication, learning to communicate. And so people are addressing this in a multi-agent setup.
Nice.
Of course, you mentioned GANs. There's actor critic, which is a generalization of that. That's also, you can think of it as multiple agents. People are looking at multi-agents, adversarial, non-cooperative, or cooperative agents. And I imagine we're going to see a lot more of it in the next coming years, especially in environments like Gandhi showed today. That's a natural place where you would want to have lots of agents interacting.
So there are some very recent, also growing body of work on dialogue systems. So basically, it's maybe not a vision task, but it's another very good example of basically modeling some interacting agents. So it's quite clear to me that if you can learn a model of this opponent or whoever you are talking to, it will probably make it easier to take some action so that you can achieve some desirable goals. So if you have a specific goal in mind or task, maybe you're collaborating with the other person or agent, and understanding how this person or agent will behave, that actually helps you to plan ahead. Possibly some idea could be combined in the visual setting, so but maybe there's some future work.
I should add that earlier Jitendra mentioned Alison Gopnik and I mentioned Elizabeth Spelke as probably two of the people on this planet who know the most about babies and what they're capable of doing or not. It's although it's more debated, but it's thought of as one of the core knowledge. So if you Google core knowledge Spelke, SPLK, you'll find a lot of information on this, and it's one of the things that the nativists believe we're born with.
Communication ability? Are you talking about communication ability?
The social
right,
ability,
okay.
the ability to immediately engage.
Right.
So we have the agency module, because even if you see two dots and one pumping the other dot, you immediately think that one dot is being mean to the other dot. So we have that. Like for 8-month-olds show that from what I vaguely recall from classes or one of the talks. And the social part is also seems to be, it's very, I mean, 8-month-olds can manipulate their parents very easily. I have to.
Anything to say about it?
Can you pass the mic on?
Speaking of simulations, I really like the AI2 Thor dataset. I also like the affordances on objects. I was wondering what all of your roadmaps are for sort of bringing together those two things so that you can, figure out the affordances of objects, given that you already have like the models, and that's really, I think, where the semantic understanding is going to come from. So I just wanted to hear your.
So I've and Vanilla are actually trying to address that exact problem. Hopefully, if you basically like just doing things and failing, you can start developing a good sense of affordances. Think about I give you a mock and I blindfold you, but just putting the different places and just even listening to the sound that you're going to hear, you can learn, you can develop a sense of affordances. So we're sort of, we call it, I don't know this term, dynamic affordances. So this is sort of a ton of affordances that you can actually learn from interaction. And I hope that we can show that we can learn those through these simulation interactive environments. We still don't have any signal for that.
And affordances is always dynamic and interactive. I'm just wondering.
Say that again.
And affordances is always dynamic. I mean, they always work through interaction, no?
Yes and no. I think there are affordances that are harder to learn through interaction, or maybe easier through label data.
So how do you define affordances?
I think it's a bigger discussion of how we define. So I think the way a lot of people have defined it, it can be basically multi-static to static and dynamic. But you're right, to reach any goal, you would have to go through interaction. That's why it's that essentially. But if you're only thinking this object affords grasping, for example. So this, you can think of it as statically, like this chair, this is the pose of a person that can sit. So if you only consider goal state, then you can think of it as static, the chair and the sitting state of the person, like a static. How do you reach to there? It makes it dynamic. And that's what I'm saying, that now that we have the whole environment, chairs in a real room, we can try to think about these goals. Because until now, that was very, very hard, right? There was no such scenes, real scenes, like AI could for example.
I think the static and dynamic are adjectives of how we're going to learn them, not the
Okay. I think we should start wrapping up. So if you have any final questions, yeah. All right.
So if in 5 years that neuroscientists will be able to do large-scale in vivo real-time recording and control on freely moving rats, so do you think such rats would be more helpful than robots for advancing computer vision?
We need to put a camera on the rat, because
yeah.
you want to know what it sees, and you also want to know what I guess you want to see the control signal of what it's planning to do or what it has done. Like what can you, sorry, I'm not a neuroscientist, so I have to ask, like, what can you record from it?
Yeah, this kind of optical coordinate control, you can basically manipulate to turn on and off each individual neuron in vivo during the free movement behavior of the rats. So basically you have kind of this real-time map of the inputs and the behavioral outputs, as well as neural activities down to very detailed level throughout the entire experiment.
I don't think we're going to have that understanding of a rat's brain in the next 10 years. Well, let's say 5 years, which is as far as I would care to forecast reliably.
Because it's not about understanding brain behaviors, but it's more about the availability of this kind of experimental setup, which generates lots and lots of data in real time and freely moving animal behaviors. And
this is very complex with a rat. A rat's brain is very complex. With the hippocampus and everything, how do things get imprinted, how does replay happen to consolidate the rat's memories. Rats are not simple animals. They're extremely smart. So they have very developed brains. So I mean, of course, science will. They can imagine that we know. They can imagine the future. They plan according to what they imagine, and they're able to do that. You know, they're a quintessential example in neuroscience for navigation and so on. After they're young, and you know, they can do almost everything we do. They don't write books. They don't have those things.
Maybe those data will be helpful for maybe understanding this, how like rat brain works, and maybe understanding some neuroscience behind it. It's not very clear whether it's going to lead something practically useful. I mean, in a sense that if you think about the task that rats are good at, maybe rats are good at navigating some maze or finding food, or but it's not like something that's like critically limiting for the current like robots. And robots can do navigation, but probably being able to manipulate objects and doing some more sophisticated like some kind of manipulation task, such as cooking or doing laundries or cleaning things. These are probably more, at least like more practical tasks, and also that it's critically limited if you consider the state-of-the-art techniques right now. So, but for navigation, maybe we are still good at doing that type of thing. So, yeah, it's not very clear whether it will lead to something practically useful, but yeah, of course it will be helpful for maybe neuroscience.
Okay, maybe one last question before we wrap up.
So first, I wanted to just comment on that I am actually doing some experiments with rats moving objects around and manipulating objects, and they actually learn to do these kind of things, and they become more efficient after a few trials of playing with it. But what my last question is about is more about the reinforcement learning part. That today, Professor Freitas gave a nice talk about reinforcement learning. But as of now, we haven't seen these systems, no matter how much complicated they become. We haven't seen them on real robots, apart from the last work that Professor Faradi was saying. And that is not even close to what robots nowadays can do. So do you think any future of reinforcement learning being actually applied in robots?
It is applied in robots. I don't know what you
No, that kind of low-level reinforcement learning.
Reinforcement learning was applied a long time in robotics. I would say at least 10 years. I don't know.
No. I'm talking about these motions that they do not require feature being handcrafted, so they come from a pixel level information. These kind of pixel to torque.
Okay.
Course. I'm talking about these.
Okay, so yeah, this is new because now the vision people are coming and they are having pixels. But really, like reinforcement learning has been applied on real robots, and yes, on the input signal that was sometimes also coming through cameras was certainly simpler or maybe handcrafted, but the entire motion, that was used in these works that I'm talking about is much more complex than the kind of motion that is currently used when we're talking about this pixel to torque thing, right? So for example, Arminow's work. It's about grasping at a particular position on a table with a particular orientation, 3 variables. Is that true? Okay, pushing, it's like, you know, how many? 5 variables. So the kind of work I'm talking about is about manipulation. It's really an entire behavior that stretches over time. And, you know, you have to control at least 7 degrees of freedom, or if you take the hand with it, it's like plus whatever. So you have like 11 and continuous, and the whole thing over time. So it's huge actually, and I agree, like the signal that you get, like the feedback, is much simpler than what's considered, for example, in Arminow's work. But, you know, it has been applied on robots. It's just that I think I talked with someone else before, that the roboticists, they're coming from complex motion generation and behavior, and basically learning this dynamic model of the motion, while the vision people are coming from, oh, these robots, you know, they're complicated. Let's make the action simple and let's encode it in like 5 variables. But we are interested in the feedback signal and how complicated it is, right? So these are 2 fields coming from different directions towards a very similar problem, and they looked at different ends, basically, of this problem, and I think it's time to merge it and to also get more complex action maybe into the picture, and on the robotic side, the more complex sensory signal.
Yeah, I would even go as far as saying some of the big successes of robotics were successes of reinforcement learning and systems of robotics. I mean, whenever, like in the early 2000s, if you were to think of that helicopter flying upside down, you know, that was a clear example of reinforcement learning meets robotics, and there were many others from Southern California and Europe and everywhere. And now more recently,
not the examples of pixels tutorials.
Well, in those days we couldn't do anything with pixels. We didn't have the computation, and in those days, in fact, we didn't even have SIFT for that matter. It came today 2 years later after those robots were flying. It's 3 years later. Now we've seen this explosion of combining RL with deep learning. And we're seeing that this is changing the deep learning architectures, it's changing the algorithms that we use for RL, new algorithms are being invented, and the sort of confluence of this being able to do computation with these much more expressive models, better representations of data and of action, is leading to a very rapid progression. The last 2 years have been phenomenal in what's been achieved. And definitely things that you do in a simulator. Actually, did you guys use A3C in your robot?
No.
So that was in your simulator.
No, really for the graphical.
Yeah. So that's a good example of transfer. You develop an algorithm that I think we wouldn't have done before because of the computational resources. You develop it in simulation. I think it started with some knowledge from Berkeley. It goes to London, it gets developed in a simulation in London, it gets transferred to the University of Washington and the Allen Institute, and eventually gets transferred to a real world. And that sort of rapid, and that happened within a couple of months, maybe a few months, it wasn't even a year. So there's some very rapid development going on right now. I think this is an extremely exciting time. There's some warnings as well that I made in my talk, that the type of policies we get with say A3C, or the things I was doing of policy versions of A3C, are still the sort of Piaget type conditioning reinforcement learning. And Jitendra mentioned in his talk, it's also important in, I think a few other people think they mentioned in the talk as well, models being able to sort of imagine, being able to go to higher levels of abstraction to do this sort of longer, jumpy type of planning into the future. That's still a challenge. We need to do this sort of more complex type of thing. Even like being able to learn many behaviors and learn how to reuse those behaviors that you learn many policies that you can reuse, being able to compose new plans out of smaller plans that you It's never been this exciting for reinforcement learning into robotics.
Great. Let's thank all the speakers and panelists again. Thanks to all the other participants, the poster presenters, and the general audience. Yeah, maybe there'll be many more editions of this in the future. See you all.
What would you do? Because your mind is down in looking for answers, it's starting to these things are not black and white anymore. This problem that I have to if you are asking me maths and I would like to when you go to actual work, Actually, you have been
second question was something oh yeah, sure. What I was asking you was, have you ever experimented sort of composing actions one to the other? Use each.
I cannot even say that I'm not obstinate also. Which is more than
robots are so complicated. It was to support because I mean, we hope for a system that can handle these low-level problems and then give us a sort of high-level interface. Yeah. Tell the robot to go fetch it.
He was so he said, I'm going back. I'm going back.
Process or maybe better learning systems. Thank you very much.
Chinese, Japanese, it's a London.
Oh, really? What's like the skill? I've seen them all right there, but I guess
Yeah, you need to know what's first comes through. So that is kind of the small details. But otherwise, so if you just have the dilating revolution, you can actually use good forward, use the climate is more with summer, like the rest of the year. Oh, there's some other states. Have you had a state here? No, yeah, no, that's the extent of that. We have crickets outside, we have, like, also. Chris, the little dog that's working on us. I see, okay. We have a state, really? Yeah. Yes, are you allowed to share? Yeah. Okay, so. Solid? Yeah. Have fun. Like I'm saying, like the fridge story. What happens if you